Right at the center of our Milky Way lurks an absolute monster, an invisible beast with a gravitational pull so intense not even light escapes its grasp. For decades, it was just a ghost in the equations of physicists. But today, we're actually looking directly at the magnetic heartbeat of our galaxy's central supermassive black hole. Welcome to The Explainer. I'm your host, Historia.
So let's dive right in. For the longest time, the ultimate puzzle in astrophysics was simply this. What does the invisible beast at the center of our galaxy actually look like? Seriously, if a black hole is perfectly dark, how do you even take a picture of it?
Our target here is Sagittarius A star, or SGA star for short, and it's located exactly 27,000 light-years away from Earth. To put that crazy distance into perspective, trying to take a picture of it from here is literally like trying to photograph a single orange sitting on the surface of the moon. And getting this shot took over a century of work. Back in 1918, astronomer Harlow Shapley first spotted stars clumping strangely toward the center of the Milky Way. Fast forward to 2017 and the Event Horizon Telescope, which is basically a global network of radio telescopes acting as one giant Earth-sized eyeball, captured the first data. In 2022, they dropped the very first image of SGR A star's glowing silhouette, and then the massive breakthrough in 2024. For the first time ever, scientists revealed the highly organized, polarized magnetic field spiraling right around it.
Wait, Historia, I've got to ask, if Sagittarius A star is in our own cosmic backyard, why did it take almost 100 years to get a picture? Especially when the team imaged that other supermassive black hole, M87 star, way back in 2019. That one is millions of light years further away.
That is such a good question. It basically all comes down to size and speed. The researchers actually described imaging SGR A star as being a bit like trying to take a clear picture of a puppy quickly chasing its tail. See, hot glowing gas orbits both of these black holes at nearly the speed of light. But because our black hole is so tiny compared to M87 star, the gas finishes a full orbit in just a few minutes instead of days or weeks. The image was literally dancing and blurring right in front of the telescopes.
And if that wasn't hard enough, there was a second massive hurdle. We have to look at our black hole straight through the flat, dusty disk of our own Milky Way. Scientists compared it to looking at a distant mountain from an airplane window, right through the hot jet exhaust. All those turbulent pockets of heated gas between Earth and the galactic center just totally scrambled the radio signals.
That sounds like an absolute nightmare to capture. How do they cut through all that chaos to see something as invisible as a magnetic field? And what actually is polarized light? Okay, let's break this down simply. Polarized light is just light that's oscillating or vibrating in a specific preferred orientation. To human eyes, it just looks like normal light, but in astrophysics, it acts like a secret decoder ring. When glowing plasma whips around a black hole's magnetic fields, it stamps a very specific pattern into the light. By catching that polarized light, scientists can literally map out those hidden, twisting magnetic field lines.
And the coolest part is what those fields are actually doing. These aren't just decorative lines. These incredibly strong, twisted magnetic fields are actively wrangling and spiraling glowing plasma right down into the black hole. They act like cosmic funnels. They essentially dictate exactly how the black hole feeds on the surrounding gas, and sometimes how it violently spits material back out.
Okay, so we've got these mind-blowing images of our black hole's magnetic fields. But how does it stack up against the big guy? Let's jump to Section 1, SGR A star versus M87 star, the ultimate heavyweight comparison. The numbers here are just staggering. Our Milky Way black hole, SGR A star, has a mass of about 4 million suns. Sounds huge, right? Well, M87 star is a whopping 6.5 billion suns. It's 55 million light-years away, while ours is relatively super close at 27,000 light-years. And remember that orbit speed we talked about? Gas whips around ours in a matter of minutes, but takes days to weeks to slowly circle the giant M87 star. So physically, these two couldn't be more different. SGR A star is basically a tiny, hyperactive toddler that's currently pretty starved for matter. M87 star, on the other hand, is an absolute Goliath, actively blasting out these immensely powerful relativistic jets of plasma deep into space.
But wait, despite those massive physical differences, the new polarized images show that their magnetic rings look shockingly identical up close, don't they? Exactly. And honestly, this is the most mind-blowing takeaway of the whole study. Gravity and magnetic processes near the event horizon are universal. It proves that Albert Einstein's theory of general relativity governs these beasts in the exact same way, totally regardless of their size, mass, or how much they're eating.
Once you get right to the edge of a black hole, gravity takes over and the physics look absolutely identical.
That is so incredibly cool. Einstein wins again. Moving on to Section 2, the future of black hole cinematography. What does the future actually hold for the Event Horizon Telescope? This is where we get truly cinematic. The next generation EHT is adding way more telescopes and observing at higher frequencies. We're moving far past just static, blurry images. The ultimate goal is to shoot high-fidelity movies of black holes in action. We'll be able to track hotspots and flares over multi-day campaigns. Plus, there's a real chance these sharper observations might finally reveal a hidden jet shooting right out of SGR A star, something that's totally evaded us until now. We are literally stepping into the era of black hole cinematography.
So the next time you look up at the night sky toward the constellation Sagittarius, remember, there is a 4 million solar mass beast spinning in the dark up there, wrapped in a glowing, spiraling web of magnetic fields. And we finally know exactly what it looks like. Oh, and a quick heads up, this explainer was generated with the help of AI. If you want more mind-expanding, dynamic stories, come find us on Instagram, TikTok, and YouTube. Just search for @30secondsofhistory. And hey, even if you don't find this exact explainer on there, we've got plenty of other incredible content waiting for you. Thanks for learning with us, and keep looking up.